morning. In the last few classes, I told you how we learned that we live in a collection of stars called galaxies, and there are galaxies like our galaxy outside our own galaxy also, and these galaxies are of different types: elliptical, spirals and irregulars. Now, there was a very important question that came up. The question was, how do we determine distances? So, today we are going to take up this question to some extent. The way in which distances are determined is referred to as the cosmic distance ladder. So, the issue that we are going to discuss is the cosmic distance ladder. The determination of distances starts from within our solar system. So, that is something I am not going to discuss. So, I am going to assume that we know the Earth-Sun distance. So, this is an issue that you should read up. How we can determine the distance from the Earth to the Sun. Okay. So, I have told you that the Earth-Sun distance is 1 astronomical unit, the radius is 1 astronomical unit, 1.5 into 10 to the power 11 meters. This distance can be determined directly, and now it can be determined directly by using radars, from radar signals, but historically people determined this from various astronomical observations. Now, so we are going to go beyond the solar system, and there is one direct method to determine distances beyond the solar system, the distances to stars beyond the solar system, and this is the only direct method. It is called parallax, the method of parallax. So, what you get using this is the parallax distance. I am sure that all of you know what parallax is. Consider an object which is static. So, there is an object over here which is static, there is an object here which is static, and the observer is moving. Imagine in a train or something. So, the place where the object appears, the angle at which the object appears changes because of the motion of the observer. This is what is called parallax. Now, if you know how much distance I have moved, from this I can determine, and if I can measure the angle which the corresponding change in the angle, then I can determine the distance to the object. This is the parallax method. This picture here illustrates the parallax method. So, this is the Sun. The Earth is going around the Sun in a nearly circular orbit, the radius of which is 1.5 10 to the power 11 meters, 1 astronomical unit. Now, consider a star over here. Now, when the Earth is in this position, the star appears at a particular direction. 6 months later, the Earth has moved here on the other side of the orbit, and the same star will now appear at a different direction. And this change in the direction can be determined relative to very distant stars. For very distant stars, this change in the angle is going to be extremely small, so small that you cannot, it is not determined, you cannot determine it. Okay, so they will appear to be fixed in the sky. So, very distant stars, very distant objects will appear to be fixed in the sky. For them, this parallax angle is going to be so small that it is going to be, it will not be measurable. For nearby stars, this change in the angle is going to be somewhat larger, and it can be measured. So, this parallax method essentially depends on measuring the shift in the angular position of a star after a 6-month period. Okay. So, we are interested in this angle theta. The distance at which, so let us say that this distance at which, distance r, at which this theta, which is half the change in the angle, this theta is 1 arc second. this distance is called a parsec. Okay, and this is the distance scale that we use beyond the solar system. So let me go through it again. The distance r at which this angle theta, so r into theta should be equal to 1 astronomical unit, and theta is 1 arc second. This is 1 arc second. Okay. So the distance at which this angle theta is 1 arc second, this distance is called a parsec. So let us determine the value of 1 parsec. So 1 parsec is 1.5 into 10 to the power 11 meters divided by the 1 arc sec in radians. 1 degree in radians is pi by 180, that is 1 degree. 1/60th of a degree is 1 arc minute, and 1/60th of an arc minute is 1 arc second. So we have to determine this number, 1.5 into 10 to the power 11 meters divided by this, the 1 arc second in radians, and this number comes out to be 3.09 into 10 to the power 16 meters. This is 1 parsec. Okay, so it is the distance at which this parallax angle is 1 arc second. This angle is 1 arc second. So the change in the angle in 6 months is basically 2 arc seconds. That's the distance. That distance is called 1 parsec. Now, from earth based observations, this parallax angles of the order of 0.01 arc second could be measured. Now, this measurement of parallax distances has been revolutionized in the 90s with the launch of this satellite Hipparcos. The full form is given over here. This shows you a picture of the satellite Hipparcos. So in the 90s there was a satellite called Hipparcos which was launched, and this satellite was launched with the purpose of measuring the angular position, the parallax angle of stars at a high level of precision. So Hipparcos could measure the parallax angle to 1/1,000,000th of an arc second. Okay, with Hipparcos it is possible to measure parallax angle to 0.001 arc second, 1/1,000,000th milli arc second. And using Hipparcos, it has been possible to measure the parallax angle, parallax distances to 1200,000 stars. So you now have a catalog of 1200,000 stars for which the parallax distance has been measured. So let us see, 1 arc second corresponds to a distance of how much? 1 arc second is a distance of 1 parsec. So if I can measure to 1 milli arc second, I can go up to a distance of 1 kiloparsec, 1000 parsecs. Okay, so we can determine these parallax distances to at most a distance of 1 kiloparsec, not beyond that. So using parallax distances, we can go from the solar system, we can measure the distances to stars which are close to the solar system up to a distance of 1 kpc at most. Not beyond that. There is no chance of using the direct measure much beyond this. So now the question is, how do we determine distances to stars and other objects which are beyond 1 kiloparsec distance? This is where the concept of the cosmic ladder comes in. So we have what is called a cosmic distance ladder. Now the way it works is, we can use this parallax distance estimate to get distances up to of order 1 kiloparsec. Now what one has to do is one has to now use some other indirect method which will start from somewhere over here and which will go to a larger distance. Okay. So we suppose you have so let me explain this to you using a definite example. So the next method is main sequence fitting. Let me explain what this method means. This method can be applied mainly to open clusters. I have already told you that there are collection of stars which you see in the sky called globular clusters. These globular clusters are very dense in the center and they look more or less like globules. You have seen picture, they look globular, very dense collection of stars in the center, and it falls off roughly of the order of 1,000,000 stars. Open clusters are different. This picture shows you the Pleiades open cluster. It is a loose collection of stars in the sky, not so dense like the globular cluster, and it has of the order of few thousands of stars. All the stars in an open cluster typically form at the same from the same collapse of the same gas cloud, from the fragmentation of the same gas cloud. So when we see stars in an open cluster, you can assume that they were all formed at roughly the same time by the collapse of the same gravitational collapse of the same gas cloud, and they have of the order of few thousand stars. Now we will digress a little bit to stars. Stars, the behavior of stars can be understood and classified on a diagram called the Hertzsprung-Russell diagram, HR diagram. Okay. So this picture here shows you a schematic HR diagram. This is called an HR diagram. Let me now first tell you what the axes have. The x-axis is the color of the star. The color of the star can be determined by considering the ratio of light in two different bands. Okay, the color is effectively the ratio of light coming in two different bands. Here it is defined as in two specific different bands. We will not go into the details. It is essentially the ratio of the light coming in these two bands. And the color is directly related to the temperature. The stars are approximately black body radiation. So the color, the amount of radiation coming in two different bands, the ratio depends on the temperature. You can see here, and the hotter the star is, the bluer it appears, and the cooler the star is, the redder it appears. So the color is something of a star is something that you can directly measure, and you can convert the color to the temperature of the star. So we can either use color on this axis or the temperature on this axis. Okay. This axis has the luminosity, the total radiation that comes out from the star. Now here again you may ask the question, how do you determine the luminosity of the star? Because to determine the luminosity you need to know the distance. What you measure is the flux. What you measure from the earth is the flux. To determine the luminosity you need to know the distance. So this brings us back to the same question, how do we determine the distance? So this can be determined directly within 1 kiloparsec by using this parallax distance. Okay, so suppose you find an open cluster within 1 kiloparsec for which you can determine the distance using the parallax method, then you can get the luminosity of those stars because you can measure the flux and you know so the distance, so you can determine the luminosity. Now if you plot these stars on this HR diagram, you will find it turns out that the large bulk of the stars lie on this curve over here which is called the main sequence. On this main sequence you have the cooler stars over here, they are less luminous also, and you have the hotter stars at this extremity which are more luminous, much more luminous. Our star, the luminosity unit is 1 solar luminosity, like I have told you, right. So 1 solar luminosity is where our star is somewhere over here, and the color here is also like the color that we see for our star or the sun, okay, roughly yellow. Now stars which are more luminous are also hotter, okay, and you can have stars 10 times more luminous, also up to 100 times more luminous. There are stars which are less luminous also, 0.1 times ours, 1/100th of our luminosity, and these stars are much cooler. This main sequence corresponds to a situation where the star is burning hydrogen. There is the nuclear reaction going on is hydrogen burning, hydrogen is getting converted into helium. That is the primary reaction. So the hydrogen is getting converted into helium, and then there is a whole chain, but this is the hydrogen burning stage of a star. It is called the main sequence. Once the hydrogen fuel gets exhausted, the star becomes a giant. We shall come to this later. It becomes a giant. So you have these red giants and supergiants here. These are cool stars, but they have enormous luminosity. They lie off the main sequence. And you also have another kind of star, the white dwarfs. These are dwarf low luminosity stars. They are dwarf because they are low luminosity, but they are very hot. So they are called white dwarfs. Okay. So the stars over here have the same temperature, but the ones over here are larger. The total luminosity is sigma t to the power 4 into 4 pi r square into the area. Per unit area it emits sigma t to the power 4 radiation, and multiply that by the area. So you can straight away say that these stars are smaller, these stars are larger. Now these details of the HR diagram are not of crucial interest right now. The way you use the HR diagram to determine distances is as follows. Suppose you observe an open cluster somewhere, then a priori you will not know what the luminosities of the stars are. What you will know is what the fluxes are. You can measure the fluxes of these stars in the open cluster. What you can measure directly is the color of the stars. The color does not change with distance. It is a ratio of the amount of light coming at two different bands. Okay. Or you can effectively, you can think of it naively in a simpler term as the color is determined by the peak of the black body spectrum, the peak of the spectrum. The hotter the star is, the peak will shift. That does not depend on the distance. Where the spectrum peaks is not going to change if I put the star further away. Okay, so you can determine the color of the stars in an open cluster from direct observations. You can determine the flux from the observations, and you know that the stars, the majority of the stars should lie on the main sequence. So you know what the luminosities should be. Once you know the color, you know what the luminosities should be. So once you have the measured flux and you know what the luminosity should be, you can determine the distance, because the luminosity, the flux is the luminosity by 4 pi r square. So you can measure the flux from the HR diagram. You know what the luminosity should be, so you can get the distance. And you can do it for an open cluster, because doing it for a single star would be risky, because it may lie off the main sequence also. It may be a giant, you do not know. But if you have a whole open cluster, you know that the majority of the stars should lie on the main sequence. So this curve has been determined first using the direct parallax distance estimator. Now you can use it to determine the distances to open clusters which are further away than 1 kiloparsec. So if you get an open cluster at say 7 kiloparsec, 8 kiloparsec, you can use, and if you can determine the main sequence of that open cluster, you can use the HR diagram to determine the distance to this open cluster. So this has extended the distance scale beyond 1 kiloparsec. Now It would be very hard to extend this beyond our galaxy, because you need to identify open clusters, fit the stars on the main sequence, etc. So, it would be very hard to extend this beyond our own galaxy. So, there is another method which works beyond our galaxy. There are many other intermediate methods which I am not discussing at all. I am just discussing three of the methods. I am going to discuss three of the methods today. Three crucial, very important methods. There are many other methods which I am not touching upon. I will urge you to look it up and read it up yourself. Okay. So, the third distance estimator is the Cepheid variables. What are the Cepheid variables? The Cepheid variables are stars which are unstable. The luminosity of these stars changes with time. So, this picture shows you the light curve, shows you the flux or the luminosity from several Cepheid variables, and for all the Cepheid variables the luminosity changes periodically with time, and the time period could be days or weeks, even up to a month. Okay. So, the luminosity changes periodically, as you can see. So, this is a Cepheid variable with a short time period. The luminosity changes periodically with time. So, there is a period, and this has a larger period, this has an even larger period, this is an even larger period. Okay. Now, it was discovered by Antonietta Leavitt that there is a luminosity period relation. The period of a star, the period at which the luminosity changes, is not something which is random. It has a definite relation with the luminosity of the star. Okay, so this is called the luminosity period relation. So, this is Antonietta Leavitt. She was partially deaf and dumb, and it was a remarkable feat for her to make this very important discovery in astronomy, the period luminosity relation. So, this picture shows you the period luminosity relation for Cepheid variables. Cepheid variables are very bright stars, and the advantage of being very bright stars is that you can detect them in very distant galaxies. If they were faint stars, you would not be able to see them in distant galaxies, and it would not be very useful. So, the Cepheid variables are very bright stars. They are young stars. The very bright stars do not live long, so they are young stars, and as I have told you, you find these young stars only in places, they do not live long, so you find them in places where there is star formation going on. So, you can find these Cepheid variables in spiral galaxies. Chances of finding them in an elliptical are very small, because you do not have star formation taking place in elliptical galaxies. Okay. So, this picture here shows you the period. The period is in days. So, the period can go from 1 day to a week to months, and the y axis is the luminosity. So, what you see is that as the star gets more luminous, its period, the period of its oscillation also increases, and these Cepheid variables have luminosities which are beyond 10 solar mass. This is in solar mass, solar luminosity units. So, the Cepheid variables have luminosities beyond 10, so they go up from 10, 100, 1000. So, they are very bright stars indeed, and you can see them in distant galaxies. There is another kind of stars called RR Lyrae variables. These are fainter stars, these are old stars which again have a period luminosity period relation. They are different from Cepheid variables, and these can be found in old population of stars. So, they can be found in globular clusters. Remember, I had told you that the distribution of globular clusters played a crucial role in telling us that about the true extent of our galaxy. So, the distances to these globular clusters were actually determined using these RR Lyrae variable stars. Okay. So, you see, to calibrate this relation, to calibrate this relation, you need to know the distance. You can measure the flux, you need to know the distance. So the way it works is you determine the distance first using either parallax or the main sequence fitting, and once you know the curve once you have some stars for which the distance is known, that is what is called calibrating the relation, because what you can measure is the flux and the period. Once you have a few stars for which the distances are known, you can convert that flux to luminosity and you will get the period luminosity relation. Once you have calibrated this, you can now use it to determine the distances to unknown stars, unknown galaxies. Okay. So, the C-feed variable, the luminosity period relation for C-feed variables was used to first determine the distance to the Andromeda galaxy. This is the nearest full-fledged spiral galaxy. It appears like a nebula in the sky, and a C-feed variable was discovered in the Andromeda galaxy, and that was used to determine the distance to the Andromeda galaxy. The distance is 778 kiloparsec, which establishes the Andromeda galaxy to be well outside our own galaxy. The extent of our galaxy is of the order of tens of kiloparsecs. So, this was the first full-fledged spiral galaxy for which the distance was estimated, and it turned out to be quite beyond the extent of our galaxy. So, it established that the nebulae which were seen were actually outside our galaxy, they were not part of our galaxy. Now, so once you discovered the fact that you knew that there was one galaxy, this whole thing could be used for other galaxies also, and the C-feed variable method was used to determine the distances to several galaxies. Now, let me quickly switch topic. So, we have finished our discussion of the cosmic distance ladder as far as this lecture is concerned. We shall come back to it possibly again in a later lecture. Let me shift to a different aspect of galaxies. Now, if you take the radiation coming from a galaxy and send it through a spectrometer, you can determine what is called the spectrum of a galaxy. So, this picture here shows you the spectrum of some randomly chosen galaxy. Now, people who are experts in spectroscopy, they can look at these spectral lines. Now, if you look at the spectrum of this galaxy, it is essentially the combined spectrum of the stars in the galaxy, and also there is a contribution from the interstellar medium. Okay, so, it is the combined spectrum of the stars and with the contribution, absorption possibly from the interstellar medium. Now, you can see that there are very distinct lines in the spectrum, and people who are experts in spectroscopy, they can identify the lines. So, the lines in this spectrum, several lines have been identified. So, once you have identified the lines, now okay, let me come back to this. Once you have identified a particular line, say calcium or oxygen line, from experiments on Earth, one knows the wavelength at which the radiation in that line occurs. So, if you have calcium or oxygen at rest and you look at that spectral line, one knows from experiments on Earth at what wavelength, what is the corresponding wavelength. So, this is the wavelength at which the emission wavelength corresponding to that particular line. Excuse me. Let us just focus our attention on a particular line. So, spectroscopists can identify the line, and we know from experiments on Earth that the wavelength corresponding to that line is lambda emitted. Now, in the spectrum of the galaxy, that particular line may occur at a different wavelength called lambda observed. It may not occur at the wavelength that you expect it. If you were to see that same spectrum line from, say, oxygen at rest with respect to you, you may observe it at a different wavelength lambda observed. The question is, how do you interpret the shift in this wavelength? This is something I had discussed in the last class also. This shift in the wavelength can be interpreted in terms of the Doppler shift, the Doppler effect. What is the Doppler effect? So, this is a source of radiation. It emits radiation at a wavelength lambda emitted. Now, if this is moving away from the observer is over here, this is the galaxy from which the radiation is coming. So, inside the galaxy the radiation is emitted at a wavelength lambda emitted. Now, if the galaxy is moving away from this observer with the speed v along the line of sight, then the observer will see the same radiation at a wavelength lambda observed, which is lambda emitted into 1 plus z. Z is referred to as the red shift. Okay. And so, this so we write this as lambda emitted into 1 plus z. This z is very important, it is called the red shift. The wavelength increases if the source is moving away from the observer, and the increase in the wavelength z is v by c. Where v is the radial component of the velocity. If the galaxy is moving in this direction, perpendicular to the line of sight, to the lowest order there will be no change in the wavelength. Okay. To the lowest order, to the linear order in v, there will be a change which is proportional to the radial component of the velocity, and we will get a red shift if the galaxy is moving away from the observer. You will get a blue shift if the galaxy is moving towards the observer. So, red shift z, which is positive, means an increase in the wavelength, and the red shift is v by c, or the velocity is z into c. So, if you can measure the spectrum from a galaxy and you can determine the shift in the wavelength, this information can be used to determine observationally the velocity at which the galaxy is moving either away or towards us. Now, Edwin Hubble, astronomer in the early 20th century, he made this remarkable discovery that the galaxies on the average are moving away from us. Not only are they moving away from us, they are moving away from us with a speed which is proportional to the distance. This picture shows you a Hubble diagram. The main point here is that on the average the galaxies are moving away from us with a speed that is proportional to the distance. This is a modern version of the same finding, that the galaxies are moving away from us with a speed proportional to the distance. This finding is called Hubble's law, and Hubble's law is possibly the most important discovery in modern cosmology. It is the finding that the galaxies are moving away from us. On the average, all the galaxies are moving away, and the speed at which they are moving away is proportional to the distance. Now, there is a point which I should make over here, a note of caution. This Hubble's law is not a very precise kind of a thing. It is not that if you whatever galaxy you take, you expect it exactly to follow Hubble's law. There are aberrations. For example, the Andromeda galaxy, the galaxy is the nearest full-fledged spiral galaxy, is not moving away from us, it is moving towards us. And in the future, our galaxy and the the Andromeda galaxy are going to collide. Okay, so Hubble's law is valid on the average. So, on the average, the galaxies are moving away from us with the speed proportional to the distance. There are aberrations, there are deviations from the Hubble's law, and these deviations are also very important, and we shall come to the interpretation of these deviations later on. Okay. So, let us now restrict ourselves to Hubble's law and forget about the deviations for the time being. What the Hubble's law tells us is that the galaxies are moving away with the speed proportional to the distance, and this constant of proportionality is called the Hubble constant or the Hubble parameter. It is called the Hubble constant or the Hubble parameter. So here I have written down Hubble's law. V is equal to h naught r, and you can, from these observations of redshift, from the observations of redshifts, what you can actually measure is just the radial component of the velocity, but we assume that that is the only motion of the galaxy. So Hubble's law we will interpret Hubble's law to mean that every galaxy has a motion which is radially outward and proportional to the distance. So it is we are making it a vector law, and this constant of proportionality is the Hubble parameter. It is currently believed that the Hubble parameter has a value 70 kilometers per second per megaparsec. It is often customary to write the Hubble parameter in this way. In units of 100 kilometers per second per megaparsec. So the value of 70 would correspond to this small h equal to how much? 0.7. Okay. So it is often customary to parameterize the Hubble parameter in this way. The subscript 0 here indicates that we are referring to the present value of the Hubble parameter, and the subscript 0 we shall use throughout to indicate the present value of any quantity. So h naught means the present value of the Hubble parameter. Okay. So this is an observational discovery, and it is possibly the most important observational discovery in cosmology, and this was made in roughly 1920s. So by 1920s it was known that the galaxies are moving away, 20s it was known that the galaxies are moving away from us with the speed proportional to the distance. It is an observed fact. Okay. Let me go through the steps again. The distances were determined using Cepheid variables, and the speed was determined using the spectrum. From the spectrum one could identify spectral lines and get the redshift. From the redshift you could convert it into the radial speed of the galaxy. So distance was known, speeds were known, and Hubble found that the galaxies are all moving away from us on the average with the speed proportional to the distance. This was Hubble's observational discovery. Now very interestingly, at roughly the same time in the early 20th century, people were, Einstein in the early 20th century, Einstein had proposed his now famous general theory of relativity. The general theory of relativity is the theory of gravity, and it basically says that gravity is a geometrical effect. It affects the geometry of space-time, and through the change in the geometry of space-time the motion of objects get changed. So gravitational field is there in the curvature of space-time. So people had this theory for gravity, the general theory of relativity, and having discovered this, the scientists were now trying to apply this general theory of relativity to the whole universe, which is what cosmology is all about. So the theoreticians were trying to make a theoretical model for the whole universe, and this model was based on the general theory of relativity. So they took the general theory of relativity and they were applying it to the whole universe. Now when you try to make a model for the whole universe, how does one go about it? That is the important question. Now if you remember, earlier attempts by Europeans to model our universe had proved disastrous to some extent, because these models had been centered on man, anthropocentric. Early models built particularly by the Greeks and later adopted by the Christian church, they believed that the earth was the center of the universe and everything, the whole universe revolved around earth. This whole thing, the whole model was basically centered on man, anthropocentric, right? Anthropocentric means centered on man. And this had proved disastrous because it had to some extent nearly brought the progress of science to a halt. It had got converted to a kind of dogma, and that dogma had come into conflict with actual observations. So now in the 20th century, when scientists again were trying to make a model for the universe, they wanted to avoid this anthropocentric point of view, which had been so man-centered point of view, earth-centered point of view. And they made certain assumptions which were as far away from this as one could get. And these assumptions go by the name of the cosmological principle. So let me now discuss the cosmological principle. The cosmological principle were the theoretical the assumptions invoked by the theoreticians in their attempt to model our whole model the universe. By universe we mean whatever exists. So the basic assumption in the cosmological principle is essentially the assumption that the universe is homogeneous and isotropic. Let me repeat again. The cosmological principle is the assumption, basically two assumptions. One, the universe is homogeneous. Two, the universe is isotropic. And it is possible to formulate this in a rigorous fashion in the framework of general relativity. But right now, let us not go into that. Let us get some kind of an intuitive feeling for what we mean by the statement that the universe is homogeneous and isotropic. So this picture over here shows you a part of the universe. Bear in mind that the universe we refer to all that exists, and I cannot show you obviously the whole of the universe in a diagram. So this is just a part of the universe. So I am showing you here a part of the universe. Now what do we mean by homogeneity? What we mean by homogeneity is as follows. Take three different observers sitting at different places, observer A, observer B, observer B, C. If the universe is homogeneous, it should look identical to all observers, irrespective of where you place the observer, here or somewhere else or at some other place. The universe should appear to be identical. That is what we mean by homogeneous. Okay. For example, let me just take an example of something that is homogeneous. Let us take a bucket of water, and inside the bucket of water, the density of the water and all its properties, we can assume it to be the same at all positions. So this is an example of something that is homogeneous. It is not entirely homogeneous because there is the boundary and beyond which there is no water, but that is one example. Take another situation where we have whole of space filled with an electric field that looks like this. Same constant electric field looks like this. Uniform electric field. And let me ask you the question, is this homogeneous or not? The whole of space is filled with the electric field that looks like this. Is this a situation which is homogeneous or is it not? How do you determine whether something is homogeneous or not? consider an observer over here and consider an observer somewhere else. Is there any difference between what this observer sees and this observer sees? No. So is it homogeneous? Yes. So this is homogeneous. So wherever I sit in this electric field, I will see exactly the same thing. That is what we mean by homogeneity. It is exactly the same at all positions. Now let us come to the next point, which is isotropy. By isotropy, what we mean is that the universe should look the same in all directions. So let us consider this observer A over here. For this observer A, the universe should appear the same in all directions, whether this direction or this direction or this direction or this direction, everything, the whole universe should appear the same. That is what we mean by isotropy. Let me again ask you a question, is this electric field isotropic? No. Why not? Because there is a preferred direction. The direction, the electric field has a particular direction. So this direction is different from the other directions, because the electric field points in this direction. Okay. So this is not isotropic. Now whatever exists in the universe, we believe the cosmological principle says that the universe is homogeneous and isotropic. Now one thing we can straight away rule out is the possibility that the universe has a boundary. Let us consider the situation where the universe has a boundary. Suppose that this was our whole universe, that is all. If this was the whole universe, then there is a boundary. Now once I have a boundary, you see the universe is no longer homogeneous. Why is it no longer homogeneous? An observer close to the boundary will see something which is different from the observer, and from the observer located over here. This observer is close to the boundary, this observer is far from the boundary, right. So the boundary imposes a preferred position, and once you have a preferred position, you no longer have homogeneity. Similarly, it also violates isotropy, because at this point there is a boundary over here, but there is no boundary over here. Okay. So you cannot have a boundary for the universe. That is something that is straightforward, follows straight away from the cosmological principle, from the assumption that the universe is homogeneous and isotropic. The universe cannot have a boundary. Now the simplest possible model without a boundary. What is the simplest possible model without a boundary? The simplest possible model without a boundary is where the universe is infinite. It extends till infinity in all three directions. It extends till infinity here, here, or in the third direction. So this is the simplest possible model where the universe is infinite. Now you also have a possibility of a finite universe without a boundary. Let me briefly explain this to you. We shall come back to this later when we take up different cosmological models. So in two dimensions, I can have R2. R2 is the plane, X, R is the real line which extends from 0 plus minus infinity. R2 is the plane, it again extends all the way to infinity. But in addition to R2, you also have a space called S2. This is the two-dimensional sphere, the surface of a ball, for example. Now the surface of a ball, we are working in two dimensions, so we are living only in the surface. The surface of a ball has no boundary. If I start from this point and proceed in this direction, I will again come back to this point. If I proceed from this point and move in this direction, I will again come back to this point. So the surface of a sphere is an example of a space that is finite but has no boundary. Similarly, in three dimensions, we could have R3, the usual infinite three-dimensional space, or you could have S3. This is a three-dimensional sphere. It's a little hard to visualize, but we shall come back to this. To some extent, we shall discuss this later. Let us, for discussion's sake, restrict ourselves to this three-dimensional infinite universe. Bear in mind that the universe could also be finite, but have no boundary. Okay. So we have, we now can discuss the model, the expanding model of the universe, the expanding universe rather. This is a very important conceptual issue which you should appreciate. So there are two inputs which go into making this model. The first input is Hubble's law, that the galaxies are all moving away. We see the fact that we see the galaxies all moving away from us with the speed proportional to the distance. This is the first input. It is an observational input. The second input is the cosmological principle that the universe is homogeneous and isotropic. Now interestingly, this discovery, the person who made this discovery was not aware of the theoretical of the cosmological principle, and the people who were working with the cosmological principle were not aware of Hubble's law of expansion. So these were two mutually exclusive things, lines, and if you put these two together, which was done later on, you are led to a model for the expanding universe. Now what is this model, this picture that we have, the expanding universe? Now let me give you the argument slowly. The universe is homogeneous. This is an assumption. Now if the universe is homogeneous, we expect the universe to be filled with galaxies, because we are sitting in a galaxy and we see galaxies around us. So if the universe is homogeneous, it should be filled with galaxies. So the first thing that you have to visualize is a universe, is an infinite universe. We are dealing with only the infinite universe. So just visualize an infinite universe which is filled with galaxies. Roughly 1.1 galaxy per megaparsec cube. This is some rough number. 0.1 galaxy per megaparsec cube. So one galaxy in a cube of 2 MPC. One galaxy in a cube of 2 MPC. Okay. So visualize a universe filled with galaxies like this. Okay. I think let us stop the lecture here today, and we shall continue. I shall explain to you the expanding model of the universe in the next lecture. The point which I should like you to just bear in mind is that from the assumption of homogeneity, we expect the universe to be filled with galaxies. So just try to visualize an infinite universe which is filled with galaxies, roughly uniformly distributed. Okay, with this, please keep this picture in mind, and we shall continue our discussion in the next lecture from here.